Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures for paper 1 in the semester 1, Electricity and Basic Electronics. This is the 30th lecture. In the earlier lecture, we have learnt the characteristics of diode, how a diode works in the forward bias and also in the reverse bias. The characteristic curves for a diode also we have learnt. And in this lecture, we are going to recapitulate what we have learnt in the last lecture, and also we are going to see the forward and reverse bias. Along with that, the rectification of a diode, how a diode can be used as a rectifier. Let us see today's session outline. In this session, we are going to see the diode characteristics recapitulation and then how diode can be used as a rectifier in two different modes, half wave rectifier and full wave rectifier, and also we are going to get the expressions for efficiency and ripple factor for the two rectifiers. Let us recapitulate what we have learned in the last lecture, the diode characteristics. In the last lecture, we have drawn the characteristic curve for a diode in the forward and also in the reverse bias. We learned in the forward bias, a diode conducts the current, and in the reverse bias, it does not conduct the current. It is a one-way device, and it could be compared with a valve that opens in one direction. All that we have seen in the last lecture. And let us have a look at the characteristic curve that we learnt elaborately in the previous lecture. And this is the diode characteristics. The typical diode characteristics for forward bias and the reverse bias will resemble this curve. In the forward bias, as the voltage, applied voltage across the diode increases, the current also was increasing. And in the reverse bias, there was a minimum current. However, reverse bias voltage we apply, the current was found to be at a constant value, which was in the microampere range. And when we compare this diagram, which was a practical diode characteristic curve with an ideal diode characteristics curve, we will have a diagram which is shown in the right hand side of the typical characteristics curve. And this is the ideal characteristics. It shows when the voltage is above the threshold voltage, the diode conducts the current in the forward bias, and in the reverse bias it does not conduct current. So, this diagram is the characteristic curve for a ideal diode. But however ideal it may be, a diode will have both the majority carriers and also the minority carriers. So, there will be a slight deviation from the ideal characteristic curve that we have seen just now. So, in a nutshell, what we have learnt altogether is A diode conducts current in one direction when it is forward biased, and it does not conduct current in the reverse biased mode. What is the application of this one-way conduction of current by a diode? We have certain electronic circuits which very much makes use of this one-way conduction property of diode. The basic application is found in a circuit called rectifier circuit. Let us have a look at the rectifier circuit diagram. What is a rectifier? Rectifier is an electrical device which converts an alternating current or voltage into a direct one by allowing a current to flow through it in one direction only. The junction diode in the forward biased condition has the property of offering low resistance and allowing current to flow through it. This property is used in the process of rectification. So, rectification is converting the alternating current into a direct current. In the previous lectures, when we learned the current electricity concepts, we have given much importance to the direct current only. We have not come across the concept of alternating current very much, but the higher secondary level idea about the alternating current is enough to understand the concepts that we are going to see here in this course. As it is a degree course, the concepts which are already familiar to us as far as the alternating currents are concerned are sufficient for us to understand the concepts in this degree program. And what is an alternating current? It has the potential at a particular point varying between two maximum values. We call such a voltage as a sinusoidal voltage. The sinusoidal voltage is also called as alternating current. The direction of current flow is also varying. It is a to and fro flow of charges that is happening at a particular rate. So, that is all any movement of charge is called current. So, here the back and forth movement of the charge is also called current. And this direct current, when we take here the flow of charges in one direction, the average flow when we take over a period of time, the flow of charges in one direction. So, an alternating current can be converted into a direct current by using a rectifier. Because the diode has the property to conduct current in one direction, that property could be used for the rectification purpose. Let us see what are the types of rectifier circuits. There are two types. One is half wave rectifier, the other one is a full wave rectifier. This circuit shows an half wave rectifier circuit. A circuit which rectifies half of the AC wave is called half wave rectifier. The circuit components here we have are very familiar to us. This is a transformer circuit. The left hand side coil, the P1, P2 terminals that represent primary coil, and it is connected to an AC source. This is how we represent an AC power supply. And on the right hand side is the secondary coil, and it is a step down transformer. As it is written, the number of turns in the secondary coil is less than the number of turns in the primary coil. So, the voltage is reduced, and when we have a look at the diagram, especially the secondary coil which is connected across a load here through a diode, a single diode is connected, and across this load we measure the voltage, and this is the ground connection, which is a common connection at for many of the parts, and here we measure the voltage variation. And what is typically happening in this half wave rectifier? As we know, the two terminals of the secondary coil of the transformer will have a change in polarity with respect to the frequency. So, the 2 points P1, S1 and S2, they will be having a change in the polarity as the alternating voltage varies, the sinusoidal voltage varies. So, let us see how the diode is behaving for a changing polarity case. For example, let us take the terminal S1 is positive for a while and then S1 will become negative. So, there are two cases that we need to consider. The first case is when S1 is positive, what is happening. The second case is when S1 is negative, and simultaneously we should remember one more thing. When S1 is positive, the terminal S2 is lower or negative. So, let us see what is happening in such a case. During the positive off cycle of the input, the AC voltage Vs at S1 will be positive and the diode is forward biased and hence it conducts. During the negative off cycle of the input, the AC voltage Vs at S1 will be negative and the diode D is reverse biased. Hence, the diode does not conduct, no current flows through the circuit. So, this clearly explains how the diode is getting forward biased when the point S1 is having the positive voltage and how it is getting reverse biased when the terminal S1 becomes negative. The same point S1 becomes positive for half of a cycle and negative for the other half of the cycle. So, alternatively, the voltage of the point S1 or the potential of the point S1 keeps varying between the positive value and the negative value. And as we have connected the diode at the point AS1, the diode is getting forward biased for half of the cycle and it is getting reverse biased for half of the cycle. So, for the forward bias cycle, it conducts the current and for the reverse bias cycle, it does not conduct the current. And what is the outcome of it? Let us have a look at the diagram which explains how the rectification is done. The voltage drop across RL will be 0. Hence, no output is obtained in the reverse bias. It is a continuation in the reverse bias case. Thus, corresponding to an alternating input signal, a unidirectional pulsating output is obtained. And here in the diagram, this is the input. The first part is the input voltage, which is a sinusoidal wave. For every 2 pi phase, the wave is repeating, and this is the DC voltage that is obtained as the output. For the positive half of the cycle, the diode was found to be forward biased, and for the negative half of the cycle, the diode was found to be reverse bias. So, no current was found, no voltage is found here, and when we compare these two waveforms, only the positive half cycles appear in the output. That is why this circuit is called as an half wave rectifier. Only the positive half cycle of the input voltage appears in the output. And what is the other rectifier? Is it possible to convert the negative part also to appear on the inputs and on the output side? Let us learn the concept of full wave rectifier. Let us have a look at the diagram to learn the full wave rectifier. The circuit that rectifies both positive and negative cycles is called a full wave rectifier. When we look at the diagram, it is more or less the same as that of the half wave rectifier, except for small modification that we need to do on the secondary coil connections, and the terminal S2 in the previous case was directly connected to the ground, but in this case it is also connected to another diode D2. So, we have two diodes D1 and D2, and D1 and D2 are tied to one point, they are connected, and then we have a common connection at the point VDC, and the load is connected between the common point of the diode, and the ground or the neutral part is taken from the center of a secondary transformer coil. And what does that mean? The secondary coil has 3 connections, S1, S2 and a center part, that is referred as the center tap transformer. We have the model called center tapped transformer. From the center of the secondary coil, a connection is taken and it is readily available in the market. So, a center tap transformer could be used to design a full wave rectifier, and it is a must. We need to use a center tapped transformer. It will have 3 connections in the secondary side, and because we are using 2 diodes here connected to the extreme ends of the coil, what is happening? Our aim is to convert the negative part also to appear on the output, but on the unidirectional way. Let us have a look at the diagram and understand how this D1 and D2 conduct the current when the alternating voltage appears across the 2 terminals S1 and S2. The same diagram again. When the terminal S1 is positive, the diode D1 is forward biased, and similarly when the terminal S1 becomes negative, the S2 will become obviously positive. At that point, the D2 diode, second diode, is conducting the current. So, whether the S1 is positive or negative, there is a possibility for current to appear at the common point where the 2 diodes are connected. Let us see how these 2 diodes D1 and D2 get forward biased and reverse biased in a particular way. When the terminal S1 of the secondary coil is positive, the diode D1 is forward biased and it conducts. Hence, there is current flow in the load resistance. Now, D2 is reverse biased, but that is not taking part in the conduction process, as D1 is already conducting the current. Similarly, when the terminal S1 is negative, D2 obviously is forward biased, and now also there is current in the load resistor. Now, D1, the first diode, is reverse biased. Thus, in the 2 possible ways, the diodes are conducting current and continuously there is a current flow across in the load resistance, and that produces a change the voltage across the resistance. Let us see how the waveforms appear in the full wave rectifier circuit. Both the positive cycle and the negative cycle appear in the output, but on the positive side, and 0 to pi, this is a positive cycle, pi to 2 pi is the negative cycle. Both the cycles are appearing on the positive side of the output. Because the variation is happening only on the positive side, it is considered as a direct current or direct voltage. When we consider the direct current or direct voltage, what comes to our mind is the voltage or current should remain constant with respect to time. Is it happening like that in this case? It is definitely not. There are ripples formed in the output form. Ripples are the variations, the change in the voltage that is happening on the output voltage that we are getting, output potential that we are getting. But can it be called as a DC voltage? Because when we say DC, only a constant value comes to our mind. But here, what thing we have to consider here, let us have a look at the diagram to understand that. Here DC, the direct current, means it is the positive side, only the positive side is meant by DC here. But even if it is the positive side, there are lots of variations still happening on the positive side, but we call that as DC because the negative part is eliminated. When it is called as DC, a straight line needs to be obtained in the output side. That is done using filter circuits. Those filter circuits we are going to learn in the subsequent lectures. So, at this point, let us not worry about the ripples that are formed on the positive side of the output waveform. But let us give importance to one thing, that the waves or the variations in voltage or current is happening only in the positive cycle, positive side of the output wave. So, thus we say the alternating current or alternating voltage is rectified as the DC voltage. About the ripples, let us not worry now. We will be able to smoothen the ripples using some filter circuits. Those we are going to learn in the coming lectures. But at this point, we need to learn some technical terms. What are the technical terms? Wherever we give some input and obtain an output, we are interested to know a particular physical quantity called efficiency. Is a rectifier circuit having efficiency? Definitely yes. Wherever you have input and have output taken, there is efficiency calculation possible. In this circuits, rectifier circuits also, we give AC voltage as input and obtain DC voltage as output. So, definitely there is a possibility for calculating the efficiency. Let us have a look at the calculation for efficiency of these two circuits. First, efficiency of a half wave rectifier. The general definition for efficiency is the output divided by input. Here what is taken as the output? It is the power that is taken across the load. So, power in the load, which is nothing but the output, and in the denominator we have power input. So, we give the AC as the input and DC as the output, but this DC is a peculiar DC, only the positive cycles are appearing in the DC power. When we recapitulate what expressions we learn in the alternating current at the school level, here the power DC is the current across the load. It is power is I square R, that we have learned in the current electricity topic. So, it is I square R, that I is the DCI. The suffixes denote L is the current load. So, current in the load, which is the DC part, and it is squared, and also the load resistance RL. And what is the DC part that is present? It is the I across the load, which is the maximum value. We know the current has the peak value and the RMS value. The RMS part is sometimes referred as the DC. So, this is taken from the earlier knowledge, earlier concepts. So, we directly substitute the values and get the final expression for DC power output. And similarly, the AC power that is given in, which is given as the input, is also I square and low and the resistance. But here the resistance is, the load resistance is considered, and also one more term called RO is taken. We can consider this RO is offered by the secondary circuitry part, the connecting wire, the coil, because the coil has got many turns. So, definitely that will also offer some resistance, hence that is also taken into account. And here the current in the load is considered, which is the AC part. So, this is the expression for the AC part that is given in. So, we get this as the expression. When we take the ratio and simplify further, we get a numerical value 0.406 divided by 1 plus the ratio RO RL divided by RL. And RO could be normally neglected because it is the resistance offered by the secondary coil and also the resistance. Compared to RL, RO is very small value. So, what ratio we have here is a very small value which could be neglected. So, we finally settle down with the value 0.406 as the efficiency. The efficiency is denoted by the term eta, and we can write the same efficiency as percentage. We have to multiply this numerical value with 100 and write it in percentage. So, it is 40.6%. So, what is the efficiency of a half wave rectifier? Just now we have derived the expression for the efficiency. We get 40.6%. percentage as the efficiency. The efficiency will be definitely less than 100%, or in a numerical value when we say it is definitely less than 1. So, it is 0.406. The efficiency is very much less. So, some amount of the power is lost in the rectification process. Obviously, we could understand the reason, because we are not getting the negative part of the input in the output side. That is why there is a vast reduction in the efficiency. Will it increase in the case of full wave rectifier? Definitely the answer is yes, because in the full wave rectifier, the negative part of the input is also appearing in the output. So, let us see how we are getting the expression for efficiency in the full wave. Before we go to the derivation, there is a small factor called ripple factor. As I said, though it is called the DC, it is not a straight line. There are lots of bumps or the ripples obtained. So, because of that, we define one more quantity called ripple factor. What is the ripple factor for half wave rectifier? There are some standard equations for that. Let us have a quick look at it. Ripple factor of half wave rectifier, by definition it is denoted as gamma. By definition, it is RMS value of AC component divided by DC value of the load, and this is how we settle down with the ratios, either the voltage or the current we have to take. This is the load in the AC current in the load, and these are some standard values that we have already got, and based on that we get the ripple factor as 1.21 for an half wave rectifier. It is a technical term normally used in the rectifier circuits. Now, let us quickly have a look at the efficiency for full wave rectifier. We can learn the concept of efficiency for a full wave rectifier in the subsequent lectures. Now, let us see the summary for today's lecture. In today's lecture, we have seen the diode as a rectifier, the concept of half wave rectifier and full wave rectifier, and also the efficiency and ripple factor for half wave rectifier we have seen. In the coming lectures, we will see the efficiency and ripple factor for full wave rectifier, and we can see whether the values are enhanced compared to the half wave rectifier. And before we wind up the session, let us have a look at the questions and try to understand how much we have learned, and try to answer them and check how much we have understood the concepts. What is rectification? Why is a diode used as a rectifier? Explain the working of half wave rectifier and derive its efficiency and ripple factor. So, with this we wind up today's lecture and see the concept of full wave rectifier efficiency calculation and ripple factor calculation in the following lectures. Thank you.